One or two?
1 and 2 hours.
Two, between 1 and 2. So let's see, 1, that's 12, that's 1, that's 2, so somewhere around there. I do not have the coordination to differentiate between, say, 130 and 120. So if you want to narrow that down, go for it, but
132.
132 I can do, no. One in every crowd. Any other speculation?
Like 1 a little bit closer to 1.
A little closer to 1? Why don't we just say 1? Because
Yeah, that's it.
this is a lot of fun to do in the biology classroom. My first year here, they had me in a biology room, lots of glassware. I was doing something similar to this last time I taught middle school. Hopefully the last time I ever teach middle school. And I did not hit Scott, just want to put that out there. Did not hit Scott. I came closer to hitting Scott than I intended when I threw something, but I did not hit him. He exaggerated. That was first period. Fourth period comes in, one of the students comes in and says, Dr. Fox, I heard you hit Scott this morning. No, I did not hit Scott.
As you should.
Is,
Probably deserved
Nobody
it.
likes
I was waiting for the phone call. I understand you hit Scott, but his mom was quite aware of Scott's desire to exaggerate the drama.
Scott
All right.
Probably deserved it though. Let's be
No.
honest.
He was a nice kid. Most of them were nice kids. They were just suffering from being middle schoolers. I've suppressed what I was like at that age. So
I suffer from being a college student.
say it again.
I suffer from being a college student.
Not as bad as a middle schooler. All right.
Oh.
Didn't used to be a problem. All right, here we go. All right, so I'm going to swing it around. I have to go slowly enough so that I still have some control here. So 6 o'clock. I'll hit 6 o'clock class. Let's do 1 o'clock. So 3 o'clock would be that way. See, that's about 1:30. 1 o'clock are right here. 3, 2, 1, go. Did not seem to hit the X. Let's try 1:30. On there. Let me know if I come close to hitting you. I guess at this point I wouldn't hear from your parents, but I'd hear from a lawyer. So. 3, 2, 1. Let's try 6 o'clock. You might want to move. Oh, back? Why don't you stand over there for this bit? Emily, I think you're okay, but just in case. So 6 o'clock. 3, 2, 1, go. Let go of that one a little bit early. And then 3 o'clock. And I think in all the times I've done this and filmed it, I don't think I've ever actually got it on film because I'm always just off camera. So 3 o'clock right here. All right. Three, 2, 1. That was the closest one so far. I think I'll go that one a little bit early. But all right. You wish to return to where you were. So what's going on? Why is what should be happening? 3 o'clock was indeed probably the best answer. Because when I let go, it should be going that way. At this point, it went that way. At that point, it went that way. Why does it seem to go in a straight line?
It's perpendicular. The radius
The spirit of what you're saying is right, but it turns out the radius and the force are not perpendicular to each other. What is perpendicular to each other? The radius and,
90 degrees.
pardon?
90 degrees.
Okay, that is, yes, 90 degrees is perpendicular,
The torque?
not the torque. What is Newton's first law of motion? That's the second.
Like,
Inertia.
yeah.
Motion tends to stay in motion.
Yeah.
If the rest stays at rest.
Things want to keep doing whatever they're doing. So when I let go, what changed? From a physics point of view, what changed as soon as I let go? Let's think forces. How did the forces change when I let go?
You lost
Tension disappeared.
tension.
Okay. Suddenly that tension is gone. Now what forces are acting on it once the tension is gone?
Weight.
Say it again.
Weight.
Okay, yeah, all right, which is down. So as soon as I let go, the only force acting on it is weight. Therefore, what is the direction of acceleration?
Down, right?
Yeah. There's no acceleration horizontally, so there's no change in the velocity horizontally. So that it will sink, but it won't veer off to the left or right because there's no force. Because things will keep doing whatever they're doing unless you force it. So as soon as I let go, it's going that way. Which means, what force was keeping it going in a circle?
Tension?
Yes. And we have a special name for that, of course. Well, first off, as I'm spinning it around, and the object is, let's say, at that point, what was the direction of the tension acting on it?
Towards the center?
That tension was acting towards the center. That is the centripetal force. It is not that other word that people more apt to use. What's the other word?
It's a fugal?
I think you said the same thing, but pronounce it differently.
Centrifugal.
Okay, and you
I
said
can't say
centrifugal.
it right.
Either pronunciation is correct. I've been told that that's the British pronunciation and that's the American pronunciation, but that could just be poppycock. But I have heard it both ways. Miss Sasson tends to say centrifugal and centripetal. I tend to say centripetal and centrifugal. She pronounces it the other way because she finds it much easier to distinguish between the two words. So, there is such a thing as centrifugal force or centrifugal force, but it is misused so often. I would generally recommend you don't use that word. If in doubt, use that one. Centripetal. Centric, meaning center. Petal, meaning
Towards the center, the direction of the center.
seeking. It is a center-seeking force, if you want to go to the root of it. What word do we have that has the same base here, the PET, that basically means seeking?
Peekaboo.
What?
If it were peekaboo, maybe. Peekaboo?
Peekaboo. Sounds like the French way.
Competition.
Say it again.
Competition.
Competition. Two teams they come together seeking each other out. Competition is from the same root. That other word, which I'll write up here and then hopefully never write again. Center. And then fugal means fleeing. What word do we have that has the same root, the F-U-G, which means fleeing?
Fugitive?
Yes, absolutely. Or if you're familiar with the Latin expression tempus fugit, which means time flies. All right. So the centripetal force, the thing that's keeping it in, is a centripetal force. Because without that force, the thing will go straight in a straight line. It doesn't go flying off out that way. If the sun suddenly disappeared, the earth will just keep moving in a straight line. Using the classic fat, dumb, and happy. Now, as said in the video, the centripetal force is not a new force. It's going to be some combination of the ones we've already done. In this case, tension is the centripetal force. Or for the pedantics, as I'm swinging it around, it's a component of the tension is the centripetal force. Because in reality, as I'm swinging it around, it's sagging some. Tension's acting that way. Weight is acting down. It's the horizontal part of the tension that is supplying the centripetal force. The other part of it is keeping it from falling onto the ground. Now, you're going around a curve. You're driving. If you can't drive, just imagine. You're driving around, as you're going around a curve, what makes it harder to take the curve without skidding?
Ice.
There's one thing right there.
Your speed.
Okay. What other crucial thing?
What'd she say again?
She said ice. So you just lump surface of the road in that.
And how the curve is, the tightness.
Yes, and that's the third one. So the three things there, the surface of the road, how tight the curve is, and how fast you're going. The surface of the road, well, what is the centripetal force? As you're going around a curve, what is the centripetal force that keeps you from going in a straight line?
Friction.
Yes.
Tires.
Yeah, tire and road. Friction requires two surfaces. So ice changes the coefficient of friction. If you flash back to some of the videos in chapter 4, it changes the coefficient of friction, so it lessens your maximum amount of centripetal force. I know F equals ma. So there's my friction force right there. Acceleration has to take the other two things into account, speed and tightness of the curve. So it has to take in speed and tightness of the curve, generally called radius of curvature. So if I have something rolling like that, that has a long radius of curvature. Something like that has a very tight radius of curvature, or small one. So as the radius of curvature gets bigger, is it easier or harder to take the curve?
It's easier.
So as R gets bigger, the centripetal force needed gets smaller. So whatever the relationship it is here, as it gets bigger, this gets smaller, so R is in the denominator. So we have this acceleration here. Centripetal acceleration. R is in the denominator. As the speed increases, easier or harder?
Harder.
So as the speed goes up, you need more force. And then, for not a reason I'm explaining, it is actually v squared. It's the speed squared. There's some nice, elegant proofs, but beyond the scope of this course. There it is.
You found that?
Oh, yes, yes. All right, so as I'm going around the curve, let's think about the velocity, because remember that acceleration is the change in velocity over the change in time. So at this point, my velocity is in that direction, perpendicular to the radius, or generally spoken as tangent to the curve. And then a moment later, you're now in that direction. If I'm maintaining a constant speed, those vectors are the same length. This would be my v initial and my v final. I know my change in velocity is just my final minus my initial. So my v final is just v initial plus my change in v. Which makes sense. I start out with something, I change, I end up with something. From a vector addition point of view, I'm going in this direction, my vi plus delta v my vi plus delta v gives me my vf. The direction of delta v is the same direction as my acceleration, which is towards the middle. So I can write my formula for centripetal acceleration as a vector. Centripetal acceleration as a vector is equal to v squared over r, and then if I want to indicate towards the middle, negative r hat. I hat, j hat, k hat, we decide the direction of two of them. The third one is set up by right-handed system. R hat is a unit vector, thus the hat. This is the radial unit vector. And it points away from the center. So if I mean towards the center, I just throw a minus sign in front. The minus r hat means towards the center. So we can't, there's no decision about, let's see, which way is r hat? The only decision we get to make is what center are we talking about? And in these type of problems, there's only one center of a circle. So, questions to hear? All right, so the way this is what we're gonna do now, I'm gonna go through two sample problems and then we'll take a break. I'm gonna grab a different piece of equipment because I grabbed a tube that was too small, and then we'll see how close we can actually get. And it won't be that good. But we're going to pretend that we're going to run a small little experiment here and see how close we can get to matching that the centrifugal force is indeed mass times acceleration. So the problem. A side view. I have a table here, and there's a hole in the middle. I have an object here on the side attached to a string, and the string is attached to some mass down below it. This is we'll call this M1 and M2. So side view. Overhead. We got a table here. I got a mass that's spinning around. There's the hole in the middle, and I got a string that's from here down into the hole. All right. So the distance from the center to here, so the radius of this spinning mass, why don't we make it 0.5 meters? E long. Mass 2, we're going to make 3 kilograms. And mass 1, we're going to make 5 kilograms. We are, of course, going to make the table frictionless. So no friction. U sub K equals U sub S equals 0. That's horribly written. U sub K. That is only mildly better. It looks like an 8 now. That's also an equal sign there.
What does that say?
U sub K equals mu sub S equals 0. That's the coefficient of kinetic friction equals the coefficient of static friction, which is 0. It's the shorthand way, apparently not
Saying
short
there's no
enough,
friction.
shorthand way of saying frictionless.
Okay.
So the only force acting on this mass is coming from the string. Sorry. There is a normal force and weight acting on it, but they'll balance out. What I want to know is how much time, how long does it take for mass 2 to go all the way around the circle once so that M1 does not move? So M1 is at rest. So let's just say V1 equals 0 meters per second, and it's going to stay that way. And what we're trying to do is find T. Now I'll put a capital T there instead of a lowercase t because this mass is going around in a circle again and again and again. Capital T is the time to do it once. It is known as the period. Time to